In this installment, we are going to make the connection between simple harmonic motion and waves. Oftentimes, simple harmonic motion and waves are taught as two separate and distinct topics rather than being a connected topic. But they're actually very much connected with each other, and we'll see by the end of this series of videos. So whenever we have something undergoing simple harmonic motion, we know it's an oscillation. So something that produces oscillations can produce waves. When there are disturbances, or we might call driving forces, they can affect the material medium around them. Material medium, the stuff, the matter around them. And they can carry that energy outward. So in this first video you would see here is a pulse. Let's imagine that this device here, we can jerk it up once and bring it back down. It would send a pulse, sort of like a whip. A pulse is a single oscillation. It's just one up and down, and that's it. It's a burst. But if it became periodic, and let's say it had a constant period, and that driving force were applied over again in a common period, constant period, we would produce a wave like this, which is called a transverse wave. If we put a line going through the equilibrium or starting point, we call this our equilibrium point or our zero, we can see then that it oscillates between this value and this value. And I'd like to make the connection that this would be XO and minus XO. So right off the bat, this has starting to look like simple harmonic motion. If we were down at this end and couldn't see the wave coming toward us, all we would detect would be motion going back and forth, side to side. And we would call it simple harmonic motion. So one way to think about a wave really is it's translated simple harmonic motion, like so. And of course we have wavelength, Greek letter lambda. It is the distance in meters between corresponding parts of a wave. So if we said that this was 0, we could map this out, and this could be 2 pi radians. And then this would be pi. And this would be pi over 2. And this would be 3 pi over 2, and we would recognize this as being a cosine function. So we could see this as a wave. It looks like a cosine wave. But also remember, we have that same motion going on here. We have the same motion going on here, and so there's a separate equation that describes what's happening vertically with it in this direction. And so that's a periodic wave. Waves that require a medium or material are called mechanical waves. And this is can be a somewhat important distinction. And these are different from, say, electromagnetic waves, which are light, or gravitational waves. All of these, and that's gravity, all that these two require is just space-time, the fabric of space-time. But mechanical waves can only pass through material, like rock or dirt or sand or air or water. They require a material medium to pass through. So let's talk about a transverse wave. We have, in this case, let's say this we could view it as like a rope made up of a bunch of connected beads, perhaps, and it's held tight at this end, and this end is free to move. And so we have a driving force up and down, up and down, back and forth, and that driving force is perpendicular to the direction that the wave will travel. You can see that if we did this with the wrench up and down, it would produce a wave that would propagate along that direction. So we have the driving force, F, in this direction, and the direction or the velocity in that direction. They're perpendicular to each other. And so that's what defines a transverse wave. Trans means across. And so you can see that these two cross each other. They're across from each other. Now, as I mentioned previously here, if we had a strobe light attached to this spring in one particular place, like one of these green dots, and we watched it as this wave propagated through, what we would see is that green dot would move just back and forth, back and forth, back and forth. And again, we have our equilibrium 0 and our XO and our minus XO down here, corresponding to the amplitude. Now, I want to make a distinction here. When we look at this wave, we are looking at a picture of a real wave. And if we started our cycle here at time 0, and the corresponding part of that wave is here, this would be 2 pi. This would be pi, and 3 pi over 2, and pi over 2 radians as that cycle goes. This would follow, as we can see when in this cycle, this axis, this horizontal axis, we're describing it as where it is in the circle, but it has an axis of, it's x in meters, and this axis is y in meters. But if we were to graph this from this vantage point down here, the blue vantage point, and watching this simple harmonic motion go back and forth, we would have a graph that would look like this. At time 0, it would be at 0. And then it would proceed. And so in this case, we'll call this y and this t, because this graph is depicting motion back and forth in the y direction. It's a yt graph, and it's actually a graph over time. This is a time axis. This is a position axis. But when we look at a wave like this, it's both dimensional. Meters, meters. The slope is 1, or the slope is dimensionless. The slope of this graph, however, is velocity. The slope is velocity here. M is dimensionless. So we can model one-dimensional behavior back and forth on a line over time, and it can appear sinusoidal, cyclical. That is different from looking at something that is varying and looks like a wave in 2 dimensions. So we want to be careful of that when we look at those 2 different types of graphs. In the next video, we will look at longitudinal waves in a similar fashion.